is saying that the diagram shows the relative position of the two identical light spring, right? Both in equilibrium. So you have this two diagram shows the relative position of the two identical, please take care of this word, two identical light spring. So it means whatever the spring constant of this spring will be same as this constant. So these are the identical light spring, both in equilibrium. So both are in equilibrium. Okay, so the spring are supported. The springs are supporting loads of mass 0.2 kg and 1.0 kg as well. So first, before proceeding or before reading the next statement of the question, I want to explore this information, right? So what I want, see, its mg should be vertically downward and its spring force will be vertically upward as kx, right? You know, correct? See, natural length, see,
Yes.
there will be some natural length for both the spring that will be the equal, so we can assume that this is the natural length. This is the natural length condition, right? For this, this much will be the elongation in the first case. You have suspended a load of 0.2 kg, so there must be some elongation, some deformation in this first spring also. So I'm indicating this as a very little one, and in the next one, this much is the total elongation. Just this much is the total elongation, correct, from the natural length. So in the
Yes, sir.
first case, we should write our equation. At the equilibrium, my mg should be equals to k times of x. What is the x? X is this deformation here, or we can say this is the x1. It means the deformation for the first spring. Is it okay? Now we have the mass, we
Yes.
have the g, we have the okay, so let's substitute the value as well. So this is the 0.2 into 10 should be equals to k times of x1. Are you getting what is the x1? X1 is the deformation in the first spring, correct? Let us write the equation for
Yes.
the second block. So the second block will have the weight of mg again, so I can write here the with value directly. So it is the 1 into 10, that's the m into g, is equals to k. K will be the same because both the springs are identical, and it has the
Mm.
deformation of x2. See, deformation is calculated from the natural length, right? This is the equilibrium, equilibrium position, but I am calculating from the natural. So let us suppose this is the x2. Is it okay?
Yes, sir.
Now, see, what is this 4 centimeter? What is this 4 centimeter? This is the difference in the height between the two equilibrium positions. See, this is the first equilibrium position and this is the second equilibrium position. So this is the difference between two equilibrium positions, right? Can we find the x1 from the first expression? Can we find the x1 from the first equation? Yeah, so this is the 2 upon k. Is it okay? 0.2 into 10 will be 2 upon k.
Yes,
From the
sir.
second expression, we can find the x2. It is the 10 upon k, correct?
Yes,
Correct?
sir.
And please see, suppose this is my natural length. Suppose this is my natural length. So x1 is till here. This is the x1. We got the value of x1. From here to here, this is the x2. We have the x2. So can we find how we can find this gap? I want to calculate this gap. So this is what, x2 minus x1. Can we say that this this gap is x2 minus x1? Can we say that this gap is x2 minus x1? Are you getting my point?
Yes, sir.
So now I will equate this with 4 centimeters. So that's why I have calculated x1 and x2. So I want to find x2 minus x1, and this should be equals to 4 centimeter. Correct? Before this, all the values are in the meter.
Mm.
You know why? Because see, mass is in SI unit. K I am taking it as SI unit. So x, that is the deformation, that should also be in a SI unit. So x2 is 10 upon k minus x1 is 2 upon k. So x2 minus x1 is equals to 4 upon 100. You should write 4 upon 100 meters. Now we have the same denominator. These are the like fractions. So we can take k as a LCM. So you will get 10 minus 2, that is the 8. You can write it directly here. It is 8 upon k. So we have 8 upon k is equals to 4 upon 100. So we can simplify this for 2s are. So I think k is equals to 200. Are you getting? We got the value of k.
Yes,
Do you know what should be
I
the
understand.
unit of k? What should be the SI unit of k?
Mm. Newton per meter.
Very good. It should be Newton per meter. Super. Excellent. Now I will try to read the next statement. The same two spring are now connected in parallel and supporting a 2 kg mass as shown in figure. So now I want to discuss, do you know the combination of spring? There is a very little concept here, that is the combination of spring. Combination of spring. Let me discuss combination of spring. See, basically we have two type of combination. One is the series combination and another one is the parallel combination. What's the condition for parallel combination is, the condition for parallel combination is deformation should be same. Deformation should be same, right? Let us take an example first for the parallel combination. Suppose the very simple case is, we have this spring and we have this spring, and their natural lengths are same, and I have attached a block here, right? So when I will extend, when I will pull this block to here, what do you think? The deformation will be same for both the spring, isn't it?
Yes, it will be the same. So,
Yeah.
but then what about the force acting on each spring?
Sorry.
So then, how would you calculate the force acting on each spring?
We will see. We will see. First, let me discuss this. Okay. See. So, okay. Let us see one more good situation here, and you have to tell me, are they in parallel or not? This is the first spring having spring constant k1. This is the block, and this is the second spring, and they are connected in this manner. This is the k2, and this is the spring having spring constant k3. Can you tell me, are these three springs are in parallel or not? What do you say?
So K2 and K3 are in parallel,
Very good.
but
K1 is not in parallel, right?
K.
No, basically all the three are in parallel. See how? When you will displace this block, suppose I displace this block by some x amount, right? So my block comes here. So now please find the deformation. See, this K2 spring gets compressed by x amount, correct? This K3 also gets compressed by x unit. This K1 gets elongated by x unit, isn't it? See, it's correct that two are compressing and one is elongating, but I'm talking about the deformation. I'm not interested in elongation or compression. I'm only saying that the deformation should be same. So now you please tell me, are you getting that all the three springs having the same deformation?
Yes, sir. I understand that they have the same extension. Yes,
Yeah.
yes,
So basically here all the three springs are in parallel, and if you have the parallel combination, in that case K equivalent is K1 plus K2 plus K3. It is opposite to the case of, with the case of resistance. It is opposite to the case of resistance. In resistance, this formula applicable for the series one, but in case of spring we have the opposite formula. So the parallel combination, the K equivalent is K1 plus K2 plus K3, like this. Is it okay? Are you getting my point?
yes, sir, I
Okay,
understand.
now you can ask your doubt. You were saying, you were asking that how we can find the individual force, or right?
Yes, sir.
So now see, you see spring force is F equals to kx, right? Suppose this has a spring constant k1, this is a spring constant k2, right? So for that you should have some, you want to find the force, so you should have this k1 and you should have this x, so you can find your k into x individually, right? Yeah, Sanuka, please tell.
Yes, sir.
Now please see for the series one, what's the condition for series one? As I told you, the condition for the parallel combination, that the deformation should be same. Do you know what is the condition for series combination of the spring? So for the series combination of the spring, the condition is deforming force should be constant. Please see, deforming force should be constant or same. We can say deforming force should be same. What does it mean? Please see. Suppose I have this spring K1, then there is other spring, both are attached with the k2, like this, and we have a block of mass m and we have applied a force f here. So please see, first of all please check it for the parallel combination. Do you think that both the spring will get the same amount of deformation? Do you think that both the spring
Uh,
will get the same amount of deformation? No,
so that
obviously no.
they'll only get the same amount of deformation if the spring constants are the same, right?
Yeah, but we are considering this as a different. So if K1, K2 is different, so we are very sure that the deformation is not going to be the same. Is it okay?
Yes, sir.
Now let us see the second point. do you think that the deforming force is the same in both the spring?
Yes, sir.
Yeah,
It
very
should be
good.
the same.
Yeah, because it's a light spring. Please take care this word. This is true only for a light spring, just like a light rope. I think you light string, light rope. When you have a light or massless string, then only the tension at each point is same. Do you know this? So this is only true for the light string, or you can say the massless string. Similarly here, this is true for light spring. That should be a massless spring, right? So in that case, basically the force along the force on K1 and K2, spring 1 and spring 2 will be the same. So in this case, you can say that yes, your springs are connected in a series connection, and the F and the K equivalent for the series connection is 1 upon K equivalent is equals to 1 upon K1 plus 1 upon K2, just like the opposite of resistance combination, or we can say just like as the
Uh,
capacitor combination. Yeah, please tell me. Any doubt? Any doubts, Anuka?
no, sir. I think I understand now.
Okay, let us see the question now. See, these are the only theories. Now we will see. First of all, please see this figure and let us try to analyze. Do you think that these two springs, let us suppose this is the K and K, both are equal, are connected in series or parallel?
Sir, parallel, sir.
How? Any logic?
Sir, because they would undergo the same extension or deformation.
Yeah, basically they are in parallel as well. And what about the deforming force? What about the deforming
Sir,
force?
that would, sir, because the two springs are identical, that means it will be equally split, right?
See,
Between each
basically
spring.
deforming force is also same, isn't it? See, mg. See, mg, whatever the mg applicable here, that will be also on this part and this part, isn't it?
Yes, sir.
So, okay. So basically this is in both, you can say. Okay, what we have to find in this parallel arrangement. Now, see, this is the parallel arrangement, not the parallel combination. Please see, arrangement is different thing, and the scientifically, or we can say the according to theory, it may be different thing. Okay, in this parallel arrangement, what is the total strain energy in the spring? Yeah, do you know what's the strain energy?
So that is deforming
Yeah,
force
that is
into
the half.
extension divided by,
Yeah, please tell.
so half into F into X, where X is the extension.
Yeah, half into x, or we can say half kx square. Correct.
Yes, sir.
So
Yes.
now, see, we have to find k. We have the k. No, we have to find here the K equivalent. See, basically we have the two spring, right? So basically we have to find the K equivalent. So if we consider it as a parallel combination, so parallel combination, we have the K equivalent is equals to K1 plus K2, and we have the value of K. What's the value of K? It's 200. So basically it is 200 plus
200.
200, that is the 400. So this is the 400, whatever the unit. And X, how much X now I will have? So see, now, the meaning of equivalent is you can replace these two springs by a single spring equivalently, and this is the same block of 2 kg. Now you have the spring constant as K equivalent. So apply the equilibrium condition here. So the mg, that is the 2 into 10, that is the mg, should be equals to K times x, that is the K equivalent into x. So please write, this is the 20 upon K equivalent is 400. So this much your x. So it is 1 upon 20. We are getting 1 upon 20 meter as a deformation. So now I will substitute here. So this is half, k is 400, and x squared, that is the 1 by 20 into 1 by 20. So I think this 20 gets cancelled out. So we are getting 1 by 2, that is 0.5 joules. Is it okay? I think that is the C1. Yeah,
Yes.
Sanuka.
Yes, sir. I understand.
Yeah, very good, very nice. So basically my aim is not only to solve this. My aim is to explain the required theory as well. So that's why I have gone in such detail, so that you get the missing part here. Okay, I think it is clear to you now.